Okay, so today I am going to talk about mole ratios and stoichiometry and how to calculate them in a balanced equation. So we're going to start out with simple pieces. Hopefully I can finish this all in a short video, but if not, I will do a second one. So when we have a balanced chemical equation, it's going to look something like this. And we have blanks in the front for our coefficients is what they're called, but it's telling us our ratios. So I underlined everything in green, and so that green stuff is just how much stuff I need versus how much stuff I'm going to produce. So it's just telling me an amount, and it's in moles is what it's referring to, which we've talked about moles, and moles is a weird chemistry concept that we kind of relate to like a dozen, but it's an amount. So whenever I say I have a dozen eggs, you know the amount of eggs I have. It's the same concept when I say I have a mole of ammonia. It's an amount. It's a certain amount. It's a set amount. And it's a number. It's not a weight or a mass or a volume. It's a number. Because I could say I have a dozen eggs. I could say I have a dozen cars. A dozen eggs and a dozen cars do not weigh the same. They do not take up the same amount of space. But it's the same amount. I have 12 of each. Same thing with a mole. A mole of ammonia versus a mole of nitrogen are not going to take up the same space. They're not going to weigh the same amount, but I have the same amount of each, which is 1 mole, or Avogadro's number, which is 6.02 times 10 to the 23rd. So think of a mole like a dozen. It's a number. That's all it is a number. And this is telling me how many moles. Okay, so I have 1 mole of this, 3 moles of this, 2 moles of this. Now then, the stuff that's in orange is your stuff. So whenever you think about like baking, baking does this. Baking follows this exact recipe, this exact setup. So if I'm baking, I'm going to say that I need, 2 eggs, 2 sticks of butter, 3/4 cups sugar, 3/4 cups brown sugar, 2.5 cups of flour, and all of these things. That's going to make 1 batch of cookies. And a batch of cookies, if I make my cookies a certain size, it's going to come out to exactly 2 dozen, 24 cookies. But it's saying I need this amount, this amount, this amount to get this amount. If I change one of these amounts, I have to change all of them, or else it won't turn out right. It won't happen. Same concept here. I need this amount of this and this amount of this to make this amount of this. If I change one of these, I have to change them all, or else I'm going to have some left over, or I'm not going to be able to make what I want to make. So that's all this is saying. That's all any of the chemical reactions are saying. It's just telling you how much you need. So like in baking, we can half things. We can double things. If I don't want to make 2 dozen cookies, I could half everything. I could grab 1 egg, 1 stick of butter, 1 1/4 cup of flour. I could just half all of my recipe, and then I could make half as many cookies. If I wanted to make more, I'm throwing a big old party. I just double my recipe. Whatever I do, as long as it's proportional, as long as the rates stay the same. So not rates, ratios. As long as the ratios stay the same, then you're good. What I mean by ratios, I mean how much of one thing to another. You all know about ratios in class. They talk about ratios. I know my my little brother-in-law, my husband's little brother, chose the school that he went to based off of ratio of girls to guys because he wanted to meet someone. So he was looking, and it was like a 3-to-1 ratio. For every 1 guy, there's 3 girls. Is that school only have 4 people? No, it doesn't. It has tons of people, but they take those ratios and they stay the same. So this is a 1 to 3 to 2 ratio. So if I doubled this and made it 2, then I have to double this to keep the same ratio, 6, and that would be 4. I'm going to write it out for you in just a second. But before I do that, we're going to break it down. So what this equation is actually saying without all the color, it's saying for every 1 nitrogen, because there's nothing in front here, so that means it's a 1, I need 3 hydrogens. So I need 3 hydrogens to produce, to make, to create 2 ammonias, 2 ammonias. Okay, so that's all it's saying. It's saying that. That's what I need to make that. If I double it and I want to use everything, then that's what I'm going to need as well. So, before I run out of time, because I can only do short videos, we're going to go ahead and try this. I'm going to rewrite the equation, and we're just going to look at the ratios. So it's 1 nitrogen plus 3 hydrogens is going to yield 2 ammonias. So I just rewrote the equation right here for you. So this is a 1 to 3 to 2 ratio is what's happening. Nitrogen to hydrogen is a 1 to 3 ratio. And then if I wanted to go from hydrogen to ammonia, it's a 3 to 2 ratio. And if I wanted to go from nitrogen to ammonia, it's a 1 to 2 ratio. If I doubled one of these, 2, to keep that 1 to 3 ratio, I need to make this 6. I need to make this 4. I could double it again. I could make this 4. This would be 12. And then this would be 8. Guess what? If I reduce these numbers down, if I look, 4 can go into 12 3 times. 4 can go into 8 2 times. So this would be 4 divided by 4 is 1. 12 divided by 4 is 3. 8 divided by 4 is 2. Guess what? 1, 3, 2. We're keeping those same ratios. That's what I mean by that. And so we're going to do that as we work problems 2. So I'm at 6 minutes, and I like to try to keep my my videos under 10 minutes. So I'm going to go ahead and end this one, and we're going to work some problems solving, keeping those mole-to-mole ratios together. Okay?